robber who or somebody who is going to print counterfeit notes. And there is always a mechanism to find if a currency note is counterfeit or it's real. So initially, what does the counterfeit guy do? The counterfeit guy basically he sees what are the patterns in an existing currency, and he tries to replicate every part of it in order to create fake currency. Now, the person who is actually doing the person who is actually doing the currency classification is looking at money, and they're basically saying that okay, this part of it is not, and he correctly identifies that this is fake currency. Now, after something is identified as fake currency, the counterfeit guy actually does a slightly better job. And then if he looks at the finer details in my original money, then he okay, this is the feature which is missing. This is the one that gave me away. And then he adds that. And again, he sends it into circulation. Again, the counterfeit guy finds it out. And then he spends more time. So every time this guy is busted, he spends more time finding what was the reason for him getting busted. What gave him away. And he tries to fill that gap more and more. Okay. So remember, in both of these setups, we required two things. One, somebody who can actually do the job, generate the art or generate the fake money. And then there is another part which actually finds if the generated money or generated art is real or fake, right? Every time the every time the person is busted, he goes back and he perfects the currency or the piece of art. So GANs follow a very simple, very similar scenario. So in every GANs architecture, there are two things going on. One, we have a discriminator system, which is shown a set of real images, and it basically says, I know what a real image is going to look like. Okay, I've seen enough examples of real images, and I'm going to save the weights which define real images. What I mean by real images is like real cats, physically taken pictures of cats. Okay, let us say that for this particular use case, I want to generate pictures of cats. The discriminator basically sees pictures of real cats, like people where they went, they took pictures of cat and then they feed it to this network. The network learns to classify every image as cat, not cat, and then it learns, okay, this is what a cat is going to look like. And then there is another part of the network in cats, which basically is generating fake images. The only job of the generator is to generate images which look more and more like cat. So every time the generator creates an image, it sends it to the discriminator system. And the discriminator's only job is to identify if the given image is cat or not cat, or it's a real or fake, or to since these are all ML algorithms, it has a binary classification, one and zero, where one means that it does look like cat, and two, where it says it does not look like cat. That's the job of the discriminator. The job of the generator is to basically keep generating images until it looks like cat. Until which point does it happen? That's the final step where the generator keeps on generating images and it forces the discriminator to classify a fake image as a real image. Okay, so success is basically when we have cheated the discriminator. Okay, this is the core of your guns. There is a discriminator which is sitting and finding if a given image is real or fake, or for that matter, if it's cat or if it's not cat. There's a generator which basically arranges the pixel information in such a way that a given image actually looks like cat. The job of the generator is to make the discriminator make a mistake, like misclassify a fake image that this generator is generating as a real cat. Now, if you look at this setup, when will the currency or when will the piece of art really look like original? Not when the generator just generates not when the forger comes up with the best piece of art. The detective should be a very skilled detective, right? The department which finds the counterfeit money, it should be extremely skilled. Only then the counterfeit money will be accepted. And the detective should be extremely skilled. Only then the forger will make a perfect piece of art which actually looks real. So, even in GANs, the job of the discriminator is not simple. The job of the discriminator plays a very important role where it should be highly trained. It should have seen like tens of thousands of real images and it should know every small detail about what is being generated, right? Only then the generator will do a very good job, and cheating the discriminator should actually be a very difficult task. Okay. So basically, GANs or generative adversarial network helps us generate new data samples by using existing data. So there are two systems at work here, two neural networks. The first neural network is the generator. The second neural network is the discriminator. Where did the adversarial component come here? The the generator wants to cheat the discriminator, right? In identifying a synthetic image as a real image. That's where the adversarial component comes into the picture. Any questions still here? Yeah.
So why would they do this though? What is the reason or intention of trying to cheat it? Is it just trying to, is it effectively just pushing the training as far as possible?
Yeah. So let us say that I think I have an example somewhere. Yeah. So this is how the network is going to learn, right? So if the it okay, I'll just explain it in a couple of minutes.
sure.
I'll come to your answer. Okay, I think it's there down some of the slides. Okay, so the first step, the discriminator sees a lot of real data. Let's say that I want to generate fake numbers, right? So the discriminator sees a lot of real images which I want to generate. Okay, so 8, 6, all of these numbers the discriminator is able to see, and it's learning a lot of things here. So the curve, so remember, it is not actually generate, it's not trained to generate a particular number. It is trained to, at least in this data set, it is trained to generate a handwritten digit, right? So the job of this whole GAN, generative adversarial network, is not to generate the number 8. The data set has all sorts of handwritten digit. So this network has the job of generating handwritten digit. That's why we are showing all the numbers. If we want to generate a fake 8, all our real data will be the number 8, right? So the first step, the discriminator actually sees all of these and it's learning what a handwritten digit would look like. Okay. And then comes the job of the generator. Now the generator doesn't have any idea of what's going on here. So what is the first starting place? As in all neural network algorithms, it is random numbers. So it starts with these random pixels. It sends it to the discriminator. Obviously, this doesn't look like any handwritten digit. So the discriminator says, okay, this is not a handwritten digit. Now the loss function will be high, right? So the loss will be high, and that loss function, it comes to the it gets propagated to the generator. Now the generator just, it doesn't know, it doesn't have any clue, any idea of why, what went wrong. So it starts arranging the pixels in some manner. So in one of its thousands of iterations, it probably comes up with some line like this. Now the discriminator still says that this is not a handwritten digit, and it says um, it rejects it basically. But the loss function is lesser. So now the generator remembers, okay, initially when I started with random samples, I had X amount of loss function. Now when I put this line, the discriminator is still saying it is fake, but the loss function has reduced. So it will remember these and it will put it into its latent space. So it will try to create more variations of this line, like a diagonal or some curve or something, or two lines together. Now again, those features they go into the discriminator. Such a shape will still be rejected, right? And then somehow again after a couple of iterations, it comes up with a curve like this. Now this curve could be a part of number 8, it could be a part of number 6, it could be a part of 3, it could be a part of 5, right? So somehow it came up with this curve and it is sending it to the discriminator, and now the loss function reduces further. And now the generator learns that, okay, all the images with curve, with this kind of shape curve, produce lesser loss function. So let me put that also into my latent space. Now it tries to combine the features that it has generated in the past, maybe a vertical line with a curve, a horizontal line with a curve. And it comes up with something like this, and suddenly this starts looking like the number 5. So now again, the loss function will reduce. And it says, okay, now this shape gave me a slightly lesser loss function. So I will just try to have this shape in my image. and it gives various combinations of this until it comes up with something like this. And now it has got two numbers, right? Number one and number five. So now obviously the loss function that it would get for this and this will be lesser than what it started with the random numbers. So that's how the generator slowly learns that learns how to combine the different features which are there in the latent space in order to produce a better results. Okay. Now the job of the now if the discriminator is really not a well thought out discriminator, right? It will accept something like this or something like this. This looks very similar to the number six, right? So the discriminator should actually be able to recognize the difference between alphabet B and alphabet 6. So it should have seen enough examples of 6 in order to appreciate different variations of the handwritten digit 6. It should have also seen things which do not look like 6 but which are similar to 6, like the letter B, right? So that's why the discriminator should be a very sharp and it should be a very sophisticated discriminator. Otherwise, what's going to happen? The generator will generate something like this, right? And it will pass through the discriminator. But the humans can actually find that this is probably not the number 6, but it is B, right? That's why we want a very sophisticated discriminator. That's why we are forcing the number through a structured discriminator, which has like a very high capacity of finding of doing the job. I think, Sudhir, I think this will answer your question as to why we want a sophisticated discriminator.
Got it. Thank you, sir.
All right. This is how the, this is basically what is GANs. Okay. One more thing in GAN is the loss function, which has like two components, which I think the group will explain. If they don't explain, I can explain it on the day of the presentation. Okay. Um, this works surprisingly well, actually. Okay. So at the starting of the generated training, it actually starts with a set of random pixels, right? These random pixels, they go to the discriminator and there is a classification. The loss function gets transferred to the generator and the discriminator. Now you see how the loss actually goes to the discriminator and the generator. So during the GANs training, the discriminator also gets even more sophisticated, right? The discriminator already has a set of weights which says that the image is real or fake. Like it knows to identify a given image. But as the GANs are getting trained, a part of the discriminator also gets updated, right? So it also gets better and better at the job as more and more variations of a given single image comes out of the generator. Now, one of the problems with generating images is, you see, we don't want the same cat image to come out of the generator every time, right? So what we want the generator to do is not come up with a single image of cat or a single example of cat, but we want the generator to develop a set of cat features which it will combine in different ways in order to generate the cat, right? That's where the latent space comes into the latent sample, the latent space comes into the picture. When you start out, the generator doesn't have anything, right? But as it goes through the training process, somewhere it says that a whisker gives me a lesser loss function. And then the set of eyes, okay, a set of eyes gives it lesser loss function. And then a set of pointy ears gives a little, again, reduces the loss function. So it basically comes up with something like this. And all of this doesn't come from a single, what do you call, a single combination. It tries different combinations of this and it learns that, okay, a cat is made up of whiskers, made up of eyes, it's made up of two ears, and made up of, a nose and all this. So every time it is generating an image, it is combining all these features in different ways so that we get different samples every time we ask for a cat image from the generator. That is extremely important in our GANs architecture. The creation of this latent space from which it is pulling out the required features which define what we want the generator to generate. Okay. Now I keep saying this right now. Um, which of this is a now given that I have told you the architecture, can you tell me
Professor,
if it's yeah.
Professor, can you tell me again about what is the final purpose of Debo's model? After they getting better, what is the final purpose of final result we expect?
Of the whole architecture, you mean?
Yeah, yeah.
Oh, okay. So GANs basically they help us create synthetic images, synthetic data basically. Okay. So let's backtrack and say if I want to generate a green pasture or ocean, right? What comes to our mind when I want to generate an image of ocean? We start with waves. We start with a beach, maybe, okay, and then we start with sand grains, texture, right, and then texture. So all these, they actually define an ocean, probably. Okay, so if I'm going to ask 10 of you to draw a picture of ocean, these five, for a couple of features will probably be part of all your images, but everything will be combined in different ways. No two images will be equal because that's the creativity, right? So if I want a neural network which will give me synthetic images, it should actually know what it is doing. Like it should know what is a ocean. It should know the features of the ocean. If it's generating a cat, it should know the features of the cat, right? So the core purpose of GANs is to create this latent space with a set of features. The ultimate job is to create synthetic images. That's the ultimate purpose of my GANs.
Does
Right?
it use primarily for visual medium for images, or does it also help in
Largely
synthetic?
for images. Largely for images, yeah.
Got it.
So the core purpose is to create synthetic images from a set of latent feature space. like what really defines a cat. So it should just pick out these things, combine it in different ways, and every time we ask it to create a synthetic image, it should combine the features in different ways and give me like an orange cat, blue cat. It should know that it should not create a blue cat basically, right? Orange cat, calico, black and white, all these things. That is the overarching purpose of my class.
Yeah, I have following up question like do the new image and video generative model like diffusor or Velt or a lot like sit then use this architecture and how like a modern LLM model, like we can type in like Green and for example, if we use the native generative the GAN, we have to input like a lot of image of cat, right? But in the new, we can like to type a prompt and how it's converts the whole process.
Correct. So, yeah, so that's why I started the class with GANs were state of the art 2, 3 years back. Um, Actually, up until 21, 22, GANs were really famous and people were all like, oh, let's do GANs. Okay. It basically creates synthetic images, right? So the LLMs and today when we generate an image using prompts, they use a slightly different technology called diffusion, uh, stable diffusion architecture. Okay, that's a slightly different. That's a very different ballgame, but that is also very resource consuming. Still, people use GANs these days for simple tasks. As I said yesterday, the real power of neural network is nowadays, at least, is in its ability to do a very specific task at low resource. Okay, so if you want the GANs to only generate one type of images every time, GANs are still very good. And even now, GANs are good for things like style transfer. Like, for example, if I have a little bit of nostalgia and I want to see what I would look like with hair on, I can give my image to a GAN and it will probably create an image with a lot of hair. Okay. Um, so for those purposes, GANs are still very useful. But you are right. The technology has largely moved towards what's called stable diffusion models for synthetic image creation.
Yeah, thank you.
Yeah. Any other questions?
Actually, Professor, I have a question.
Yeah.
So, what I'm understanding is we are using this for images to create synthetic data because images are far more complex than regular data. Is there any conceivable way where it might be useful when we are not dealing with images and very complex mathematical numbers like climate, etc.?
Yeah, obviously. So GANs can do some a little bit of music also, but the music is usually done by what are called VATs, variational auto encoders. So a variant of a neural network. GANs are also the power of GANs is really images. But it also helps in other, as I said, very complicated tasks where we want to create new patient records from existing patient records. So that way, even text data you can feed to GANs and it can actually give out new profile of patients um, for probably a rare condition or so. Yeah.
Thank you.
Any answers?
Yeah, Professor. So in this network, it is
Mm.
important to ensure that the discriminator is more strong and learning better than
Mm.
generator,
Mm.
right? Otherwise,
Correct.
okay, it would diverge. And another thing is the latent space is nothing but the noise vector which where it is drawn from, right? It is a set of
Yes.
this one. And how relevant the noise is, because it is basically the initial seeding vector for this
Mm.
network, right? And even if it is random, it is going to take some more time to arrive at the the relevant positions. Is it correct?
Correct, correct. So the randomization is only in the first few iterations. After that, it hopefully learns some of the patterns. Again, we don't know what's going on inside the latent space, but it will stop being noise vector, random vector, and it will start being a more meaningful representation within your latent space.
Okay, okay. Thanks, Rose.
And again, we are really hoping that the latent space is filled with, if you want to cat, it has whiskers, and we don't know what's there. We just hope that that's what it has.
And if my discriminator is of network, let's say, it is able to take my textual input of a description that it is a dog, which is of this type, and it is trying to compare that whether my generated image is matching that. In that case, it will become a text to image GAN, right?
Yes, correct.
Okay.
That is basically the principle behind text to image scan.
Oh,
So again, the discriminator is the real catch here actually. So the as you said, it's very very important to have a very strong discriminator, right? There are countries which have low crime are countries which probably have the best law enforcement, right? But even there things will go wrong, right? It means that criminal is really smart. So it's very important to have a very sophisticated discriminator. Only then, um, very nuanced features will be picked up by the generator.
and the learned representations, if
Mm.
we are able to distill them, it can even be utilized to find out fraud detection or anomaly detection, right?
Very much, yes.
Thanks, first.
All right. Thank you. I just curious regarding the software in real life. Do you like Microsoft or any of the softwares? When we talk about it, then when we talk about GANs, we will automatically think of those softwares. What I mean is what are the like when we talk about diffusion, we talk about diffusion models like what is I forgot. But what when we talk about GANs, what are the software or the companies that like most famous for, Professor?
Oh, okay, okay. So I think you're talking about CLIP or VITs, vision transformers, and stable diffusion models, which basically create images from the scratch, especially diffusion models. Yeah, so some of the models which are given by these big companies, they are very famous. Unfortunately, for GANs, you can actually develop a GAN. It's like, and I think in the talk it will come up. Let's see. There are people who came up with different architectures. There's like a style GAN, there's like a cycle GAN, like how Google came up with its Google Net. And then the group of people came up with VGG Net, ResNet. So there are specific types of GANs with different modifications, which basically use the same principle, but they tweak a little bit here, a little bit there, and optimize it for a very specific task. Yeah, such architectures do exist, but not from one of these big names. But it's more like what function it does, like a style GAN or cycle GAN.
Mm-hmm. So if we are a person and we want to build GANs, and we'll use like Google Colab, or like Microsoft, right? Or
Yeah, so like how we had pre-trained models in our neural network, like so today nobody builds neural network from the scratch because the BGG weights trained on ImageNet data is already available. The ResNet weights 152 trained on ImageNet data is available. The weights trained on medical data is available. So some of these weights are publicly available. You can just use it. So if I want to develop a GAN from the scratch, I would probably reuse some of these weights, GAN specific weights, which are available in all of these platforms like Hugging Face or anywhere, and I would build on top of it.
Got it. So you search it up, search online, and there are like a lot of already pre-trained, and you can start from
GANs,
there.
yeah,
Yes,
probably
like
available.
Hugging
Yes,
Face.
yes.
And regarding the cost, how is it compared to diffusion models? I would bet it might
So some
easier,
of these,
cheaper.
some of these weights are probably free actually.
Got it. Thank
GAN
you,
weights,
Professor.
Okay, so I have a couple of questions here. Now, one of these is supervised. Another network is unsupervised. Can you identify which of these networks is supervised, which of these is unsupervised?
Generator is supervised, discriminator is unsupervised.
It's the opposite, right? Discriminator is
Then,
supervised.
yeah, because a discriminator actually does a
Learn
zero
from the
one
real
classification. Yeah,
image. Yeah.
it has labels, right? So the discriminator's job is to actually classify 0 or 1. So it has seen real world images and it does the binary classification. So it has seen real samples with labels. So the supervised part is the discriminator. The generator it doesn't even know what it is generating basically. Yeah.
I see it this way. Um, the generator produces an output and which is being validated by someone that whether it is good enough or not. So it is. So I said that it is supervised. When it comes to discriminator, yes, it produces real or fake, but nobody is there to validate that whether the decision taken is correct or not, right?
No. So you see, there is a bit that which comes here, right?
But it has two parts. The discriminator has two parts, right?
It has already seen a set of real and fake images. So
Well,
it has seen label data.
yeah, we will be able to close that only for our real world general truth set. Now, when it comes to the fake images, no one is validating that whether it is doing it appropriately or not, right?
No, it is there, right? So it is doing a 0 or 1. That classification is back propagated because this is a neural network. Although I put it like this, it's actually a neural network. There is an input and there is an output. So the loss function gets propagated to the discriminator also.
Yeah, here the upper image has a general truth to perform supervised learning, whereas the lower image it never have a general truth to perform. Okay, but that is technically an inference, right?
It is inferred from the loss function.
Got it.
And part of the loss function actually goes to the generator. The generator has absolutely no labels, it doesn't know what it is doing, actually. It is
Now,
working in the dark.
yeah,
That's why it is unsupervised. There are no labels for the generator.
yeah, I accept the point that discriminator becomes a supervised learning because the upper set becomes the training data set and it gets validated, whereas the lower one becomes the inference. So for the inference, like we will not be having labels, so it has to perform the job. Now, when it comes to the generator, every time when the generator is, producing an image, the discriminator acts like a labeler, and because of that, it becomes a closed loop learning, right? So the discriminator for the if you look at the generator, it generates the image and it goes to the discriminator. Discriminator is basically labeling that it is real or fake. And now, if it is fake, it tries to improve that using that error function. If it is true, it is going to go in the same direction and improve it further. So now there is a closed loop for the generator, right?
Yeah, so the point where the generator will stop training is where it consistently cheats the discriminator, not just one time cheating.
Yeah, but generator becomes there is someone to tell that whether it is right or not. Then it is a supervised learning, right? Or
Okay, no, just because the weights are updated, it doesn't mean that it is supervised, right? So we have a clustering algorithm. There is some sort of a loss function even when we do clustering. That doesn't make it supervised. There's no explicit label there. It just identifies those clusters.
yeah, here in the Gen AI, we have a concept called self-supervision, self-supervised learning. So what we do is like there is some neural network, it takes a decision, but then there is another neural network which looks at the passage, tries to take the meaning or whatever, and it tries to create a label, and that label is used to learn. In that case,
Okay, so you are arguing that this is more self-supervised than unsupervised. Okay. Uh, I'll think about it. Okay.
Sure. Thanks, Bruce.
I'll think about it, but okay, I'll think about it and let you know.
Sure, no issues.
This is the kind of thing which just sets me off in the class. Now I can't concentrate on the class. A good thinking exercise is. I'll probably do it tomorrow when I have some time. Today I'll concentrate on this session. Okay.
No issues.
Okay. So which of these does a regression problem? Which of these solves a classification problem?
Discriminator is a classifier, the generator is a regressor.
Correct. So again, it comes down to the two basic problems in ML. So some variation of this is only you are going to see in all of your ML algorithms. Uh, um, so discriminator is going to solve the classification problem. Generator is going to be the regressor. It basically says at every pixel what is the best regression from 0 to 255. Okay. All right. So I think that's all I have here. Okay. And I think I have an example with the currency note. So when it starts, when the generator really when the generator starts generating images, it would generate something like this, which obviously is not good. All it learns at this point is there is something going on here, there is something going on here, and there is some image here, there's something going. So these things, it just learns iteration by iteration. Okay, it would start with a blank slate like this, and then it will say, okay, consistently there are this this part has darker pixels. So this will be probably one of the first things that it learns. So it will fill out the areas which appear in brightness darker than the other areas of the image. Okay. Based on that, it's going to slowly develop on that, and then it's going to say, okay, I'm going to put something over here. Okay, that gives me more error. So I will put an eye here and then a nose, and it's going to go slowly from there. Okay. Until it is able to create something that looks very like the original, very much like my original input image. Any questions? I think we had a lot of discussion and
usually the challenge comes that how to assess that a network what we have given for the generator is good enough for the GAN, because like we find that at the end of it, it's not converging. Is it? There are many possibilities. Like it could be generator not sufficient, or discriminator not sufficient, or
Yes.
some training coefficient issues. So
Yes. And imagine the GPU requirement for this, right?
yes, yes,
So it's very surprising that when GANs became really popular, people started using it for a lot of fun things like how what would a person look like if they lived in Victorian era, right? Take a person from Victorian era and put them modern clothes and see what they would look like in 2026. So these are some of the fun things that you can actually do. But it's really the diffusion models which made such YouTube videos really popular. Okay, more than GANs really. Okay, so one of the strongest applications uses for GANs is generating synthetic examples from existing data set. Like, for example, we have people with glasses, and we have men without glasses, and then we take those two features and generate a set of women with glasses. Okay, so we use these images, and transfer the glass part into these image, and we created a set of images from not from the scratch, but from existing examples. So we can these GANs, they are really good at generating human faces. So there's this website called this is not a person.com or something like that, where every time you can actually generate different see it's still available.
I think this person does not exist.
Yeah, I think that's what it's called. Yeah,
I also seen another website, bullshitgenerator.com, where
okay.
it tells like how to give presentations for executives.
Okay. Okay, so every time I refresh this site, I'm going to get a different person, and this is a completely synthetic image actually. Okay, so you would have noticed that this is not a very diverse set of faces. That largely comes from the training that the discriminator is able to pass. So, if there are no examples of people from different racial backgrounds in the discriminator, then only one set of features will be learned by the generator, right? So it's going to pull out only those, and that's why it is important for the generator to do a good job. It should actually the generator should see a lot of examples of different backgrounds and different these things. Really depends on the capability of the discriminator. That's why the discriminator is a very important part. It should be really sophisticated. Okay. Uh, yeah. So this is image to image translation is one of the most still actually used applications of GANs. So you take an input image, and then you have a ground truth, and you have an idea of what the image will look like in another scenario. Like this is a daytime image. This is again well lit, but what the same place would look like if there are no lights or during dusk. That's what this image basically says.
So what is
Okay.
ground truth over here in this example?
Okay. So ground truth is basically what the discriminator is. So when we want to do like so how will this setup look like in GAN? Okay. This is the input which will go to the generator actually. Ground truth is the image which the discriminator sees and classifies as real. Okay, so anything that doesn't look like this, it's going to say fake. So what I want done is I want the features of this image transferred to this image. So this kind of a GAN would not start with a blank slate. It would not start with random pixels. It would start by sending the input image directly to the discriminator. So obviously, the discriminator has learned dusk features like dawn, dusk, whatever, twilight features, right? So there are no twilight features here, so it will say fake. Now that will go back to the generator. Now the generator, after a number of iterations, suddenly it will change some pixels to dark here. It will make this area dark. And now the discriminator will say, yeah, now it is starting to look real. And that's how the generator would learn.
So in simple English, would this be right to summarize that you're able to replicate photo modification or image modification
Mm,
facilities at a
correct,
batch level? So it's like
correct,
creating filters
correct.
and then you apply those filters to batches of photos to fast track your post-production process.
Correct, correct, correct. That's one of the major applications of GANs.
Got
Denoising, converting black and white image to color image, filling in missed patches, restoring photos. So all these are still very good applications of GANs actually.
Got it. And does this apply to video as well or just to
So
static
yeah,
image?
you can just do it frame by frame and that becomes your video loop.
Got it.
So the GANs and the autoencoders are addressing um, the same concept in a different way. Is that correct?
Mm. Yeah, yeah.
Okay.
So we did, remember we generated new images in autoencoder also. We denoised images. The
Hmm.
same MNIST we generated, but these are two different approaches.
And GAN is technically superseded by transformer-based Gen AI. Is that correct understanding?
Yeah, but with more resources.
Ah,
The
ah,
GANs used more resources when they came actually.
yeah.
So in 2021, 2020, those time frames, GANs were very resource hungry.
Hmm.
But compared to the resource requirement of transformers and diffusion models, GANs are relatively cheaper.
But okay, the parallelism of the transformer still exists with the GAN also, right? Hmm. That wise,
Mm.
transformer is no way different from GAN.
Yeah, some of the example applications of transformers. Yes.
Hmm, hmm, hmm.
So this is exactly what one of you brought out, right? So there is an input image and there is a text output for that. Okay,
Hmm.
so this is exactly the text to image or image to text translation, where the discriminator is actually doing a classification, we're doing a multi-level classification for a single image until the generator is able to generate the correct set of features.
Professor, so for those who might not know the technology, they will generalize it as like AI generated image. But if you know
Mm.
the technology behind, you will go to say like, oh, this is GAN's image or diffusion image, something like that, right?
Yeah, so we will just say AI generated image, but there is really no way to say if GANs were used or autoencoders were used or diffusion models were used. There's no way to say what happened in the backend. You can probably give one of these options and say it's probably one of these five things.
Mm-hmm. Thank you.
Okay, image to text, text to image. segmentation, again, in the case of self-driving car, really all this uh, a lot of information is actually not required for yourself. One of the things that is actually required is proper segmentation of the areas in the image that really matter and the areas in the image that really do not matter for a self-driving car. So anything that happens here in this purple area, in this blue area, is what your self-driving car is largely going to care about. It's not going to care about an airplane which is going to fly there, right? So any movement here is not a region of interest, whereas this, and this are probably very important for self-driving cars. So it is important to generate synthetic segmentation patterns. Like we should be able to create this from this or the vice versa, this from this in order to function properly. And GANs are really, again, good at this. Okay, so converting a frontal face view to different perspectives. This is a very famous application of GAN, still very popular, very useful. Where if you want to try on different clothes, you can actually upload an image and you can see what a person would look like in a different outfit. Photo to emoji, photo editing. No, I keep saying this in every lecture, I think for 2, 3 years now. It would be really cool to have for these wedding planners to have something like a GAN where you can really upload your photo from different perspectives and what a bride would look like if they had their hair to like as a bun or as flowing hair or using some sort of a style instead of trying out 10, 15 different hairstyles in the stylist shop. It would be really cool to have something. And one of the things that I had in my wedding was I didn't know if I had to wear a sherwani or a suit or whatever. It would have been really cool if I had a starting point and I had uploaded my image into something in the wedding planning shop, and they're giving these options like, you look so stupid in your coat, in your suit. You will look less stupid in your sherwani. You will look more stupid in your white color suit or something like that, right? So the GANs really have that power in them where you can show these really, it will not be perfect, but it will be a good starting point to kind of see what a person would look like in all these outfits. Um,
The
uh,
similar examples could possibly be they currently use them for beauty and makeup. Like, what would it look like with this color lipstick, with X color lipstick, Y color lipstick? Would
yeah,
that be a similar example? Maybe even these guys like Live Space and all who help you imagine your space
yeah,
by dragging and dropping a sofa, coffee table. Would those also be relevant examples?
definitely, yes, yeah. So, how would your living space look with this particular this thing? Yeah, anywhere where there is image generation involved, we will have some sort of a GAN or diffusion model in the background. Okay, so I'm not going to. Okay, so I talked about this photo blending is again a very nice application of GAN. It takes concepts from the segmentation which we talked about and from pixel filling, finding missing places in a photograph, combines these two, and it basically combined this and this to create a particular image that looks like this, right? So it learned what is the field that needs to change here. So there are three fields here, and only one of them has this new color. Okay, so creating high resolution images, all this. I'm just going to um, you can read through this and you can um, ask any questions if you have all these applications. It will be the person who is doing GANs, the group. I hope I have not given away too much of what you wanted to say. I still hope you have enough things to talk about in your talk. If you feel that I have stolen your thunder, please write to me. We can come up with something. I'll give you some ideas as to how you can probably improve your, or what new things you can add in your presentation. Just give us the A grade. I'll help you get an A grade, but I can't just give you an A grade. So as I keep saying in all my lectures, the first thing I say is usually you have to really work really hard to do badly in my courses usually. So getting probably the highest grade might be a little bit difficult, but like if you show up, if you mark all the checklist, you'll end up with a fairly good grade. Okay, so that's usually my style. Two kinds of people need to work really hard for my class. One who really want to get like the top A plus kind of grade. The second group is really who want to fail. So you have to really work hard for both of these categories. Anybody, the rest of the group will naturally fall into the B's or A's or any of those grades. So I have to worry much about that.
Um, I have a kind of question that's bothering me in my head.
Sure.
So is it possible to use the forecast scenarios? I'm I keep thinking of, for example, if you have like you're trying to solve serial murders or some type of criminal activity by a group that you can't catch. And I just keep wondering if it's possible to translate information from previous crimes, you know, um, and then sort of try and project it into, to try and anticipate
Mm.
scenarios, to form hypothesis to catch the people. It's I don't know, it's just a crazy thought, but I'm just
Yeah,
wondering
no,
because
no,
it
it's
seems
not
like
crazy.
it seems like it's the same pattern that's being used, right?
Mhm. So, what kind of neural network can we use for this purpose, right? So, we need the data that we need for this is profile of previous crimes, and we want to find out where. So, this looks more GAN kind of a thing. Uh,
Yeah, I
was
was
probably
thinking of
created.
GANs in
Yeah.
particular. I was thinking of GANs in particular because it just seems to
Mm.
match the pattern.
Mm. Mm. Yeah. Yeah.
Or
Probably
even
we
or,
can.
or even developing business plans, or getting into a market. If you look at patterns, I don't know.
So
Sorry,
yeah,
it
yeah,
just
correct. I
seems
mean, we can probably come up with if this person were to like if we have like a profile of how they acted in a particular city, and if there is enough data, and then we can see, okay, this is what they did in New York. But if this particular person lands up in probably San Francisco, then what would be their modus operandi, right? So we are really
correct.
using an existing profile to match it to a different kind of profile, right? Different city, or if they move to a rural area from a city, what would they really look like? How would they strike, right? So yeah, it's probably possible. Yeah, probably possible. Yeah,
Thanks.
yeah. Too much stress. Okay.
Or what about crossing fields? What do I mean by that? What I
What
mean by that,
is?
okay, you know what? One of the basis of innovation is taking ideas from one field and applying it to another,
Mm,
right?
mm,
So what if I deliberately thought that there might be a pattern, an archetype in one field, found a way to encode it, and then applied it to a completely different field,
mm,
um, and try and see if I can actually find patterns, the similar patterns in other fields, and come up
mm.
with really, really innovative ideas.
It's possible in the sense, you see, at the heart of it, what do we need? What do we need? A set of weights, right? A classifier which can do a binary classification, and then a generator which can generate some sort of numbers, right? So as long as these conditions are satisfied, I guess that's possible. As long as you can do as long as a binary classification will solve the problem. Like in your first case, does the profile, what would be the binary classification, which the discriminator will do? Probably, it will just say if this is the criminal style or not. Okay, right? That's probably one binary classification that I can think of. In a second example, what would be the binary classification which the discriminator will do? If you can answer that question, and if it can save a set of weights from real examples, we'll be able to implement a GAN architecture.
Okay, thank you.
Yeah. Okay. So moving on to RNNs, the next big thing with your neural networks. Well, your CNN, your ANNs are good when they are stateless, right? So as long as you don't have to remember something, ANNs are good. But a lot of problems actually need the historical context in order to make a next prediction, like time series forecasting, your language modeling. So if I have a sentence that says, the cat sat on the dash. There are only a couple of answers which can go into the blank. You can't write ocean. You can't write light bulb. It's really hard to think of the situations where cat would not sit on something, right? um, I thought of bottle, but probably a cat is capable of sitting on a bottle. I'm not sure. Uh, and then I thought of box. Box is cat's favorite. So yeah, the if I have to fill the blank, I have to remember the words that actually came in like before the blank. The most important word being cat, right? So a lot of situations require us to remember context, at least two, three words before in order to make prediction. Right? So a memory component or a state component is actually required in a lot of scenarios. And RNNs, that's where RNNs come into the picture. Of course, I'm sure that you have seen time series forecasting as an example in a number of previous situations in your ML. But just thinking about time series, why do traditional neural networks fail there? It's mostly feed forward, right? So we flatten the input before we give a signal to the ANN, right? But flattening out actually gets rid of the context, like which word came before what kind of a thing. So it's very difficult to work with um, neural networks, traditional neural networks, when we have to remember the position of a particular word. within a sentence or a position, like day one, day two, day three, that's what is going on. If I want to make a prediction for the fifth car here, I need actually data from first 2, 3, 4 hours, right? So those temporal dependency, the neural networks are very bad at learning. Okay. So how do RNNs really help here? They have a hidden state, what's called a hidden state, and that keeps updating over time. Well, let's not worry about the jargon, but they have something that keeps changing after time. Like after hour one, something is working here, a new component gets added here, and things go into that. After the second hour, some more data gets added into that memory component, right? Which we are going to call a hidden state. Okay. So more than apart from hidden neuron, we also need to have a hidden state. State is a memory component, like what happened before that. That information needs to be captured, right? So in sentence prediction, again, we need to know what came before the. Oh, I have exactly so the same sentence. Okay. Okay, so we are basically creating a paradox when we work with the neural networks where we are using a non-temporal setup in order to study something which is actually dependent on time, right? So we need to process one word after time, and the hidden state needs to be updated in order to make a prediction. But traditional neural networks don't really work that way. So other scenarios you can use GANs for video prediction, like what would happen in the next frame. We will know that only if we have information about what happened like 2 minutes before, right? So video prediction RNNs are very useful. Sentiment analysis, text generation, stock price prediction, right? Okay. So before we go into the RNN architecture in full fledged, let us take a break just after these two slides. Okay. So at its heart, RNN is very, very simple actually. It is it is just a deep neural network, but we just make some minor modifications as to how information flows through it. Okay. Instead of just having weights per neuron, as in ANN, we are going to have weights across time. Okay. And these weights across time, they are the remembered component, right? And at a given situation, these weights are shared with the different timestamps within the neural network. So, for example, in the sentence that we started with, the goes through one part of your RNN, and then there is this very famous curved arrow which you will see in a lot of RNN diagram, which is basically the weight actually. Okay, the way to imagine the weight is being reused every time. Okay, that's what the curve little means. It doesn't mean that something is going into the neural network. Some number is being added into the neural network. No, it just means that the same weight component keeps recurring in every part of the neural network. Okay. I had a really difficult time imagining this arrow when I started doing this. Just 1 minute, please. Okay. So the same weight is being shared at different timestamps in order to make a prediction. How this really happens, that we will see after the break. Yes, Prince. Okay, your voice is breaking.
Give me a moment. How about now? Hello. Am I audible properly now? Is that
Yeah.
okay? So in earlier neural network, we were always uh, tweaking the weights as per our loss function, right? But here because it is keeping the same weight always at different states, then how
Mm,
I would be able to minimize the loss?
fantastic. So I threw a word here in the introduction called back propagation through time. So instead of traditional back propagation, we are going to make a little bit of tweak there, and we are going to talk about back propagation through time called BPT.
So it will come.
What is it?
So it will come in later slides, is it?
Yes,
Okay,
it's coming in
perfect,
later slides.
perfect.
Yes. So let's meet after the break.
So what time are we regrouping?
Okay, so let's continue. This is the famous figure that you will see when we talk about RNNs, where X is my input and okay, so you look at this equation, and if you remove this HT component, this is basically your any other logistic regression equation or any neural network equation, your weight equation basically, right? So the input times weight plus the bias term. Okay. The only thing we are adding is this V with the H T. The H is the am I audible first? I hope you guys are back.
Yeah, yeah,
Okay.
you're
All right, thanks. Okay. So the H is the hidden state component. Um, the hidden state is basically again you can think of it as numbers. It's a vector, and I mean it's a number, and V here is the vector which is actually the weight of the hidden state component. Okay, so we have our input xt at any time t, the weight for the input, and then we have the ht component. The HT is basically the hidden state which is calculated for time t. Now that is dependent on the t minus one, like what input came right before that. If that's the first word, then t minus then this whole component becomes zero. Okay. What was the hidden state in the for the previous word or the previous timestamp plus the bias term. Okay, so this equation is very similar to what we have in our logistic regression. Very, very similar. Only component we are adding extra is this HT. And the HT is basically the activation function. Is basically the output of this, and we use some sort of an weight and a bias term to get the output YT at every timestamp. So if I go back to my previous example here for the time, this thing, time series forecasting, HT will be here for the first time. So if I have to make a prediction at time t, then this will be my YT. If I have to make a prediction at the third point, YT will be this. Okay, if I have to make a prediction at this point, YT will be this, and so on and so forth. Typically, what happens is we usually don't care about the output at time two, time three, or whatever. We only care about the output which comes ultimately, like at time n, when you want at the end of 10th hour or 11th hour, when you really want your output. Okay, so usually the output that comes anywhere here that is hidden, and so you get only the YT at time n, okay, time k. Okay, so this part you will not find at every timestamp. Usually you find this as your end output or your end result, which can be your next word, next token, or the sentiment at the end of the sentence, right? So that is your YT. But this is what keeps recurring. This is what keeps happening at every unit within your RNN. Okay, so U is my input. V is the weight of the hidden component of the hidden state. W is the weight of my output. My xt is my input. Ht is the hidden state at time t. Y is my output. Okay, is that clear? We'll talk more about how this equation expands. But at this outset, I would be happy if you appreciate that this is very close to something that we already know. We are only adding a weight and a hidden state component and a weight for the hidden state component. Can I go on?
Yeah.
So now let's unfold this how and see how this keeps repeating at every time point. This has to be y. I used a little bit of inconsistent terminology throughout this, so this is y. Okay. Okay. So what really happens? This x1, x2, x3 can be anything. It can be a sentence. It can be different data points in my time series forecasting. This can be some label that I am going to get from a video feed. Okay, so that's my x1, x2. H is the hidden state. So based on the first input alone. So what happens when I really unfold it is, well, what I mean by unfolding is this is the recurrent component, right? This keeps repeating for every word. So if I, as you can see here, for the first word, there's going to be a H, there's going to be an X, there's going to be a Y, there's going to be a V for this, the U for this, and what do they call this? W. Okay, W for this. This is going to be there for all of my words. Okay. So what the
Sorry,
neural network is
Professor.
doing? Yeah.
I thought it's X is the input and Y is
Yeah.
the output.
Yes, correct.
So
Oh,
it's
yeah. Okay. So the arrow should be flipped.
yeah. Thank you.
Yeah. Okay. Or I should have the arrowhead should be flipped actually. So the is coming here and there's an output. Or I should have the words here. I'll make that change. Okay. Thank you for pointing it out. Okay. So I have my input one, which is my first word, which is usually tokenized. I'm taking the example of a sentence. Okay. And at this point, the hidden state, there is nothing much to do in the hidden state, right? Because there's no hidden state here. This is the first word. So it is making a prediction. Now, if the first word is the word the, then it can be absolutely anything in the English dictionary, right? So you would technically, the network would produce an output called Y1, but we will not be using that because we are interested in the fifth word. Okay. So if I take this example sample sentence, the cat sat. If these are the three words, internally the network is actually making a prediction for the also. That's what we see here as Y1. But we usually don't care about that because we are only interested in this, right? So that's happening. Because of the first word, something gets added to the H1. So the hidden state is created here, and that hidden state goes to the next word. So the next word to the next component in your RNN is the second input, which is the activation used to predict Y1, not the actual output. Okay, what I mean by activation is this component, this whole component, not this. Okay, so this equation, the output of this, the HT, that goes to the second input along with the weights. The weight is basically the importance that I want to give to this hidden unit, right? So weight has the same implication that we had in our regular neural network. Is it is a component. It is telling how important this feature is. Along with that, I'm adding the second word, tokenized. This is going as input for the second word, which is cat in this case. So now we have the cat. Again, a prediction is made using the same equation, right? The H2, the activation is created. After the activation is created, we have YT, which is basically a G of W HD plus a bias term. This we are ignoring again here because we are not interested in completing the sequence at this point. We are only interested in getting the activation for that sequence because we are creating the hidden state, right? So the H2 gets updated and that goes as input to the third word. So the activation used to predict W2, so the whole H, this whole output of this, the HT, that goes here along with the weight component, the V. Okay. That is used to predict the word that would come after the third word. So what we would see here is actually the Y4 when Y3 goes and then we are making a prediction for Y4. That's what we would end up seeing, but all these things are happening in the background. What gets carried over is the hidden state. Okay. So if you notice a couple of things, I think I have it somewhere. Okay, so hidden state calculation. H represents the current hidden state. U and V are the bias, the weight terms. B is the bias metric, which is the same as what you would have in your regular neural network. The output at every time point is there, and that's what we have over here. Okay, so output at time t, the activation function that I used in order to generate that output, the weight at time t, and the bias term. That's the output at every point. Okay, so the hidden state is done, the output calculation is done. Now, how it unfolds over time is this thing gets repeated for every word, right? So, as a result of that, the hidden state gets updated, and that acts as the memory, right? Each hidden state you are going to call it a unit, and the HT gets updated every time. Why? Because it is getting more and more input, right? When you had only the next token could be anything in the English language, but once you introduce the word cat, the number of words that would come next is has shrunk greatly, right? But with a three-word sequence, the number of words that are likely to come follow has even shrunk further. Okay, that's how it is learning the next token or the next word prediction using the sequence. Right? That is the recurrence component. And if you notice here, it is the same U, same V, and same W. But what keeps changing is the H1, is the HT. So H1 becomes H2, H2 becomes H3. That keeps changing, but the weights, the V, the U, and the W, they remain the same during the first forward pass. Is that clear? So during training, during the first forward pass, the V, the W, all the weights are reused. Okay, the V of H remains the same, but the actual H changes. The X1 changes. The Y1 changes, X2 changes, Y2 changes. All the what goes into the recurrent unit changes, the hidden state changes, the output changes, but the weight of all these remains the same. Okay, so it is just we are creating some sort of a recursion within that neural network where we are using the same weight within a particular unit.
Professor, I just want to
Yeah.
clarify. So the input is called X and output is called Y. In the cat set, so one of the words, like each of the word, the cat set are inputs.
Yes. So
So it's the X, right? It's the X here.
this is the
X1,
X.
X2, X3.
Correct. So this is X1, this is X2, this is X3.
Yes, and the blank is the
Oh
Y.
yeah, so it won't be Y4 actually. Sorry. So the Y4 will be the next token. We will actually see that.
Yeah, and so the blank one that we're trying to find is the Y.
Find the black, yes, exactly. You're trying to find the black,
Yes,
which would
and
be Y3 here.
since we already define the X1, X2, X3, and so that's why the limit of choice is even more limited, then it will be
Limited.
even easier to guess in this
Correct.
case.
Exactly. That's
Thank
because
you.
the hidden state keeps updating.
Mm, yeah, thank you. And so sorry for another clarification. So we input it right at the beginning, right? Or we input after, like for example, we do x1 and then h1 and then y1 with one of the calculation first, and then we input x2 and then we get to y2 and then we input x3. Would that be in that sequence, or we like input all of them at the same time right at the beginning?
Yeah. So that's the training data, right? So during training, we show a lot of examples. The cat sat on the mat, and then we say the cat drank the milk, and then we say the dog ran towards the human, right? So we have all these sentences in our training data set, right? So that's where the X1, X2, X3, all these stage. So that's why when you have only the first word the when as X1, the choice of words is actually huge. It could be cat, it could be dog, it could be anything.
Yes.
All that comes from the training data set.
Mm-hmm. So we just give the and and then and then it gets a lot of choices,
Mm.
and then we input the cat, or like the
So
machine gets it.
we don't input. We show the sentence. The network learns. The network says, okay, if I have to make a prediction only using the first word, this would be my choice of words. If I have to take the first and the second word, then this would be my choice of words. So it creates that the probability distribution for every word after that. I think I have a slide for that somewhere. Yeah, here it is again.
Mhm.
Okay, so if I take this example of next word prediction at t is equal to 1, I love deep learning. Then I have all these hidden states. And every time there is a probability of the next word. Okay, that's the probability of the next word. Where you see this distribution here. This is the probability distribution for every word in the lexicon, in the corpus. So it creates this probability distribution for every word in the corpus after looking at a given word. Did that answer your question?
Yes, I do understand. I just sorry, Professor. I think I missed from the beginning when the time when you input the next word. So the time here means like you input the first word I, and then the machine will calculate and then comes up with a lot of choices, and then you input the word love, and then they gonna predict a lot, and then you input deep, etc., right?
Yeah.
Yeah.
Yeah,
So
correct.
it calculates like every single time you input something in.
Yes, correct.
Um,
Yeah.
yes, and it's not like you input at once. I love deep learning from
Oh,
the
no, no.
beginning.
So I input, I just give the sentence. It looks at each of the word sequentially.
Oh, okay. So and
It's
then
not like
it's
I'm getting it and I'm giving it one by one. The way that I have structured my network is it is recurrent and it goes only in one direction.
So it automatically cut out each word and do the calculation and predict the next one.
Yes, that's the job of the hidden state. Yes.
Got it. Thank you.
So by the time it comes to deep, it knows probably that it could be only I love deep learning or I love deep waters or I love deep trouble. Right. So it could be one of a very few set of words, like 10 or 12 words, which is a lot because we started with probably 10,000 words here. It's come down to probably 10 words by the time it comes to the fourth.
Professor, if
Okay.
I'm having,
Yeah.
10 inputs, then it'll
Okay.
be H1 to H10. Is it correct?
Ah,
Now, H1 gets overwritten but when the H2 is generated, or the H1 retained as well as
updated.
H2
It gets
is
updated.
updated. So,
Yeah.
so ultimately, I have only one H for that element.
Ah, correct. Exactly. We are going to leverage that.
Okay, okay, thanks.
Can you explain that, Professor, what you mean by that? Because if I'm getting
Somebody is
it,
asking a question, but I think your mic is muted or
am I clear now?
yes, you are.
Yeah.
Yes.
Professor, just the concept you explained, because if I'm looking at a stock for 10 years, I want to predict it for 11th year or 12th year, right? So this would be the mechanism, right? RNN would be the one wherein I can pass the
Mhm.
10-year stocks and it will be to that. But how are we ensuring that by the time the 10th year stock, first and second year are still in memory and that is not being lost?
Ah. Because after every time that information gets encoded in the hidden state. It's not explicit, but implicitly it is there, right? Because H2 is created with H1 in mind. When I create H3, I'm not only looking at, of course, only I'm creating H3 with H2, but H2 is ultimately dependent on H1.
Got it. So in this case, we are not saying that there's going to be 10 hidden layers. It's just the repeat, the recursive that
Ah,
works. Correct?
correct, yeah, correct.
Okay.
So, Professor,
Hmm.
so should H1 is the hidden state. So H1 here represents I. Then H2 should represent I love.
Yes,
And,
that's
and
what
then
I have. Yeah.
then H3 should represent I love deep. Then
Yes.
is ah
So word
after
3 plus the activation used to predict W2, which is H2.
hmm.
So,
That's
Professor,
H3.
Hmm.
so
Yeah,
Professor,
because I
can
was
I?
referring to the slide before that. Yeah.
Yeah. So here
Yeah,
is
this
the
slide.
same thing. Yeah.
Yeah.
Yeah,
Because
correct.
I would think that H2 will be I love the two words. Then
Correct.
H3 would be I love deep. And then H4 would be I love deep learning.
Yes, correct. And
Okay.
this will probably be blank. This will probably be blank. And after deep, it will say learning based on H3. If I have a T5, then that will be my prediction. What comes here is what we are trying to solve.
Right.
If I'm trying to solve T4, then it will end here. We won't have any H4.
Right. Thank you.
So you need to give it enough words before it can predict the next word, correct? I can't just say I and then wait for an answer, correct?
Yes, that's what it's doing implicitly in the background. So it for every word, it is actually doing a y1, which is the second part of this equation. It's doing this y1, but we are not generally interested in that. We are really interested in the HT part of the Y1. We take just this part, we feed it to the next unit.
How would we know which word to provide? Or how many words to provide? You see what I mean? Because the only problem with
Because
RNN
like
is
now it is training, right? It is training using like different sentences. Now during a test time, I will give a sentence something like the dog sat dash, and then it will probably say on, because that is the only logical next word that would come that it has seen in
got
the
it. Yeah, yeah.
corpus.
That's right. Yeah. Understood. Thanks.
Professor, so I can simply understand that H1 H stands for history. History has the word before, right?
Yeah, you can think of that, but it's usually, I mean, people use all different kinds of alphabets. H is easy to relate with hidden state. So the word state is a very engineering term. They use it in a number of situations where some sort of a memory is required. So LLM, they say it's stateless. RAG, they say it's stateless. When you cache, you add a state memory. So state is a very favorite term for this place. So yeah, since we don't really know what is happening in it, instead of calling it a hidden layer, we're calling it a hidden state.
So, Professor, can I simply make an analogy to current blockchain technology? So a block is based on the previous block hashing
Mm.
to continue to deduce a value. Similar
Mm.
to the mechanism here, we are guessing
Mhm.
the words next to the other based on the history.
Mhm.
So
Mhm.
every word is based on the previous of all hidden states drive to the current state.
Yes. Yeah, really. But I would treat the blog a little bit carefully because RNNs typically work with small sentences when you have like huge corpus. Because it just we'll see what happens when you use big sentences on huge corpus.
Thank you.
Thank you. Yeah, Mathur, Ram Subramanian. I thought there was a question. Okay. The hand just went down. Okay. All right. So if I want to take another example, let me take the example of sentiment analysis. Okay. In sentiment analysis, again, if I want to do a sentiment analysis for this, again, just the task is different. Instead of predicting the next task, it is trying to find the sentiment using just one word. At X1, it is trying to find the sentiment using the word the, it's giving an output, and then I love again an output, then deep, and then after learning, there's again an output. Although all these are happening in the background, we don't get to see it because it is irrelevant to the task, right? We are not interested in the next word after at time T2, 3, and all. We are only interested in at the time 4, right? So these outputs, they get kind of suppressed. That's why I have it in light blue, but that is happening in the background anyway. Okay, because the weight is have the weights are there. The activation is there. The output you can it's do. Now, what is a situation where this will really matter? Like every output where we would want to know is something called, let us say, part of speech tagging, called POS tagging. It's a very favorite of NLP people. So part of speech is it identifies what is a noun, what is a verb, what is an adverb, what is a preposition, and all that. So as a result of that, so if I want to implement something like that, then every output is important. So what is the what is the role of the word I, right? So the output will not be the next word. It will be something like, I don't know, like noun probably. Love is probably verb, and deep is adverb, or no, learning is noun or whatever. Learning is probably verb, but deep learning needs to be a single word. So it gets complicated. But the point of POS is it identifies which part of the sentence is a noun or verb or whatever. So there, you will not be just interested in Y4, you will actually be interested in Y1, Y2, Y3, the output that comes for every word. Okay, so that is something that's going to be that's going to do the opposite of what I have on the screen, where I'm only interested in Y4, in sentiment analysis, in next word prediction, but in POS, every Y1, Y2, Y3, everything is important. Okay, so this is a use case for now why should we even do Y1, Y2 if you are not going to use it at all? Okay, there are situations where you will use Y1, Y2. Any questions?
Professor, when we have this positional encoding, it's something like with a transformer like a BERT and other mechanisms when they evolve, the NER and POS and lemmatization, stemming, all those things, it has lost its relevance. Is that correct notion?
Not completely. Um, I mean, it depends on the task, right? Instead of being a part of the pipeline by default, NER can be actually a task by itself. We would want to know what's really happening with the particular sentence, like for intent classification or whatever. We would want to know what is the named entity in that particular corpus or in a particular sentence. So it is a task specific thing rather than being a default part of the pipeline.
And for that matter, the
Having
transform.
said that,
Sorry, please go
yeah,
ahead, sir. Please go.
yeah. So having said that, any pre-processing is very task specific. Like for example, for some sentiment analysis, it might not make much of a difference if I use liking or like or will like. I mean, the like is the word, and it can be used for basic first level classification kind of a thing.
Yeah, NER also required a strong corpus, and we needed to import the set of words and then have that. But still, we used to have, if somebody has a name like a rainbow, it has, it will still be falsely classified with respect to POS or NER, right? So such kind of and transformer has multiple heads, so which can assume a function, and we can, if NER has to be performed like with the transformer engines and the pre-trained methods are already existing, we will be able to easily reuse that. So I'm just thinking, so we study NER POS to understand.
I'll come to that. I'll come to that.
Yeah,
I think I get your question. So just because embeddings came into the picture, I think bag of words did lose its relevance, right? If I want to do like even last week, I was doing I just took some corpus and I was thinking if the study is feasible or not, like if it's worth spending time. So I spent, I think, 3 hours, 2, 3 hours, building a basic, what to say, or not 3 hours probably, 30 minutes probably. And after that, I will go 3 hours. So I've spent the first 30 minutes doing a basic bag of words, a basic NER. I used NLTK library and the size SciPy library and all that to see if the study is worth doing or not. Like if I have a 10,000 page corpus, I just took 2 pages from there and I implemented something at a small scale, right? And uh, that really gave me an answer to my question, to a question in my head as to if I want to pursue this or not, right? I could have used an embedding model, but I use a bag of words because I really have control over what I do when I use bag of. I can really see the output. I can see what words are there and all that. So to answer your question, the relevance is still there when you want to pilot something, when you want to do a feasibility analysis, when you want to work with a small corpus, when you want to do something on a small scale, do like a first pass. Still, all these algorithms are very powerful. The moment we go to LLMs, cost comes into the picture. So it's really worth seeing if it's worth the time and the money that you are going to spend next 1 month.
And when we apply the transformer, it doesn't need to be an LLM, right? It is just a transformer. It's another neural network model, but it is not a complete LLM, right?
It's not a computer, but most of these powerful things are hosted somewhere, right? So when you call it, it will still cost you tokens and all that to host it in a server and all that, right?
Okay, but we can run a so for example, like a T5 can be run on our
Locally.
yeah.
Correct. Yeah.
Okay. So I understood, Professor. Like, yeah, NER, POS, and all those things, even RNN for that matter, uh, it is having a historical importance as well as the evolution to understand the purpose of.
Evolution to understand, because we are going to end with the encoder decoder model. The last
Yeah.
slide is encoder, but in order to get there, we need to understand these things. So the sequence to sequence, I have only one slide actually.
Okay.
But to get here, we need to understand where it all kind of started, right?
Okay. And my question was just to understand that are they currently in use or only in the academic material?
Um, I would still, if I want to do something that's locally hosted, where my medical data is very sensitive, right? So I can, if I can get my job done using an RNN, why would I spend my time and resources hosting a model, calling a model, spending my server this thing and all that?
Got it. Thank you.
Okay, so with one small tweak with our back propagation, we are going to change the back propagation to back propagation through time, BPTT. We are going to just, it's a very same thing that we have already studied, but we are going to deal with back propagation one unit at a time. So these are the terminologies that we already have. Updating the W is going to be pretty simple. So we are going to have the loss, and we are going to have the loss by the W weight, right? This is my first back propagation, which through which I can reach H3. Okay, so updating W is probably the easiest because it is directly related to my output. And we are working under the assumption that we did not calculate the loss at this point. At this point, we calculated the loss at this point. Okay, that's the assumption we are working. But we can actually implement the loss at any of these outputs, because at the end of it, it's only the output that really matters, right? Okay, so this is probably the simplest, the W component. And then comes updating the V. Okay, so now we have this and we back propagate. You see where V starts. V is a common component for H1, H2, H3. Okay, H1, H2, and H3. Right? So we start with W and we start with H3, update H2, update H1. Okay, but before we go there, we also have the other component called U. Now, U is there for every input word. Remember, this is a shared weight. U and V are shared across all my inputs, across X1, X2, X3. Okay, so during forward propagation, forward pass, H1 changes, X1, Y1 changes. But during back propagation, whatever changed during X1, those things they remain constant. So we have frozen kind of H3, H2, and H1 that really doesn't change. It just retrieved. But what really changes is, or not really changes affected or looked at, is your U and V. Okay, that's what your back propagation basically affects. So we have our W, which is directly talking to H3, and from H3 we go to the U component. We update the U component. Now both U and V is affecting the previous activation at this point, right? So once I have updated my W, once I've updated my U, and then I go to my V. So technically the previous lane should come here, but that's back propagation through time. Everything else is going to remain the same. So where we saw uh, by W, and then we have W by X3, and then H3 by U. And then we have the U component, which is U and V, which basically affect the activation of this whole thing. Now, this is how the weight is progressively updated. So the chain rule remains the same, right? The only thing we are adding is the H3, where it recursively it adds the this thing, updates the weight there. Yes, please.
So it's U is always gonna influence the U weight, right? So if the value of U is big, then the state of the context of the sentence will not change. Or is it gonna change? Because here U is actually taking some threshold and adding it to the previous weight, right? Is that the correct understanding? Am I audible?
Yeah, you are audible. I didn't quite get your question actually.
So, as you just mentioned that this U is actually adding some value into previous weight to generate the new weight, right?
No, U is the weight.
U is the weight, right? So,
Yeah.
so basically, how this U is getting calculated? Because uh, we
Same thing.
started with a
Starts with
random.
random. Yeah,
Yeah.
starts with random number. And then we make a prediction. If the loss is high, the weight is adjusted, U is adjusted, V is adjusted.
Okay.
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 Until and this is happening recursively. It happens first for H3, and then happens for H2, and then happens for H1.
One more thing. So, because when we say adjustment, so if this adjustment number is very small, for example, if U's value is very small, then will it
Correct.
impact the final results?
Correct. So that is actually a problem. Remember, our problem with deep learning was small number getting amplified, becoming even smaller number, right? So if the number is actually small, the problem of vanishing gradient is much higher in RNNs. That was one of the reasons people quickly lost interest in RNNs because now RNNs includes, introduced another big problem. Instead of vanishing gradients, it brought a new problem called exploding gradients. Since there are so many multiplications, yes, even a small number like 5 will get amplified because it's recursively happening, right? For one weight update, it is doing H3, H2, H1, like multiple levels, it is doing the back propagation. So the problem of vanishing gradient and exploding gradient is notorious in RNs.
Perfect. Thank you.
Yeah.
And one more thing, so because I have seen most of the utilization, especially in the where we are dealing with the continuous data, I have seen RNN is something that is used a lot, especially in the time series side. Because being into finance, I have used this RNN, but um, I know uh, because in our case, data is not so sometimes we get an optimal result, but I'm not sure that how it will behave when we have a very huge, data and where I have a very huge sentence to predict something out there.
Correct. Correct. That is a situation where your RNN might actually fail. Okay. Because, and that's actually why, because of the vanishing gradient, exploding gradient problem. Okay. This is a very simple slide. I know it looks too complicated. But the task of your RNN, it can be, or types is depending on the task. If you do a binary classification, 1 to 1, you give one input and there is a one output. Image captioning, you send one image, but you have multiple outputs. In the sense, multiple words like cat, sit, mat. Right? So three words for one image input. Sentiment analysis, you give a sequence and then you give just one output. Like how? So that's many to one RNN. There is many to many RNN language translation. So what happens? Quickly, I'll tell this. Somebody said that so H4 actually has captured the meaning of the whole sequence, right? So if I come here, I love deep learning at H4. I actually have the information about I love deep somewhere implicitly it's stored. Okay, so people leverage that and they say, okay, I will use my H4 and I will try to reconstruct the same sentence using in a different language or in the same language. Kind of like the autoencoders which we used. Conceptually, it is kind of similar where you have an encoding part, then there's a bottleneck part, and then an decoder part. Here the encoder is I love deep learning. The bottleneck part is the vector which actually stores the hidden state vector, the V component actually, the V of H4. The V is the weight which actually stores the hidden state, right? So you take those weights and you try to reconstruct in a different language. Okay, that works surprisingly well. And that is the basis for language to language translation, where you have many to many. Okay. Now, this architecture which I talked about, encoder, decoder, language translation, is your basis for all your LLMs. Okay, so that's the basis for all your LLMs. That is the final missing link through the course that we saw, and the next jump to my GPT based models, bird based models, and all that, transformer models. Okay, that is the concept. But the problem with implementing that in an RNN effectively is the size of the sentence. Now you see RNN can work with small sentences, but if you increase the sentence, how much can you suppress? How much information can you put in this one vector which is sitting here, right? The last. You can probably compress a sentence of 10 words, but not a paragraph. Then the V of H4 becomes really weak. So that's why we need something better which can code, which can preserve the concept, but which can code the sentence in a better fashion. Okay. Um, Again, these are different strategies to look at RNN. I'm going to probably skip this. But that's where LSTMs actually come into the picture. I think we are out of time here. LSTMs basically they decide they solve the problem which we had with our RNA. Okay, LSTMs have the concept of gates. The reason I keep using past tense is because LSTM is a model that came out in 1997. Okay, so how's that? 30 years old. right? So LSTM is probably whether you can call it is not even a millennial model. It is the it's probably the end of the millennial times, right? So we are using that model still quite effectively, but that really had the seed for all the further models which we are going to, which came out later. Okay, so the concept of gate was introduced in LSTMs, where we really decided what to keep, what to forget, and what to pass forward. So in LSTM, it's very, very similar to RNN. If you understand RNN, LSTM is really simple. So the concept of gate, which we had, the concept of hidden layer, which we had in RNN, evolved into a gated unit or a gated cell. Now, the gated cell coded not just what happened before in the sequence, it also made like a decision, and it said, okay, hey, wait, I have this whole sequence, but how much of it should I retain? Right? So the gated cell happens for every word within the sequence. Instead of just giving the output, it added one more component called the state of the cell. Okay, before in the RNN, every RNN unit gave one output token, right? But here, apart from the output token, we are also going to have something called a state for that particular cell. So the state acts as a memory for the long-term memory that's going to be there. This is the whole complicated diagram of my LSTM. So I have my input at time t, and there are going to be three gates here, three cells here, or three components. This is my first component. This is my second component, and this is my third component. Okay. In LSTM basically stands for long short-term memory. So the long component is this one, is a cell state or memory, which is actually, you can think of it as a long-term memory where it has the global information about that particular sentence. Like whatever is there present in that sentence, that keeps continuously coming from the previous sequence. Incrementally, things get added to that long sequence. That is the long-term memory. And then we add a short-term memory. Given this new word, how much of this new word is going to contribute to my existing long-term memory? That is the short-term memory component. Okay, so the long-term, short-term memory is what defines your LSTM, right? So the three things that we saw here, we'll look at it in detail. The first gate is what's called the forget gate. So the forget gate basically gets two inputs. There's a current word and a recent context, which is the previous, which is a hidden state, which is very similar to what we saw in RNA. So the input and the hidden state, which gives some context as to what happened, what was the output from the previous word. Okay. Now, what this very nicely does is it uses a sigmoid function to produce values between 0 and 1 and decide if a number is close to 0, this particular word is not really contributing much to the sequence. So let me forget this. And then if the number is close to 1, it says, oh, okay, this is going to be an important thing. So let me retain this. Any number in between, it just decides to keep the word partially, the context of that word partially. So the forget gate basically decides if it can remember what I have been remembering till now. Okay. And then comes the input gate. Now the input gate does something that is slightly different. It says now, given this new word, how much of this new word is adding to my existing concept, existing context, which came from my previous hidden state. Okay, so it is making a decision as to if this particular new word which is there in the sequence, how much information, how much it is contributing to the already existing sequence, right? And it decides how much of this needs to go into my long-term memory. You see the big line which keeps coming here, right? And if you see the number, it is multiplication. So if this number is 0, then the long context is actually gone. It deletes it because it decides it's not required. If somebody says my phone number is, if somebody says, I like this color, and then they say, oh, actually, you know what, I don't like it. Now, these are two contradicting things that are going on within the same corpus. So, this gate, it says, okay, I got a contradictory information. So, let me forget whatever I had. And it removes the first sentiment, which said, I like this color. And it gives more weightage to the new sentence because this is a brand new information, right? So when I multiply this number with 0, that is gone. Okay. Now I have an activation with the sigmoid and I add it to my existing long-term memory. So now it says, when it sees a sentence, actually, I don't like it. Right? First they said I like it. So it removed that context by multiplying with 0. Now it is adding to the context and it is giving more importance to it. Right? So it probably comes up with a big number here. Okay? Because it multiplies and it adds it to my existing concept, existing context. That's what the input gate does. So it says this particular word is going to be very, very important because it just changed the whole direction of the sequence. And then comes the output gate. The output gate basically says, basically gives like a token prediction and a hidden state to the next word to process. That's all. The output gate doesn't really do a lot of these complicated things. Okay, so the output gate basically decides what information from the LSTM should go to the next one, which is basically your HT information. So, but what it has based this information on, it has taken this decision based on the current internal memory and what came right before it. Right? So it gives the whatever it has done in this previous state in the input gate, it activates that and it gives it to the next word. These are the three gates. The first gate remembers, decides if the long-term information is worth retaining or not. The second one decides how much is this new word contributing to my long-term sequence. The third gate basically returns the activation that it has calculated in the input gate, and it gives some workable thing to the next word within the sequence. This is the core of your LSTMs actually. Did that make sense? If you understand RNN, LSTMs are really simple. That's why I spent more time in RNN. The hidden state basically became the memory cell here with a little bit of tan-rich activation and sigmoid activation and all that. That's all. Yes, but
Professor, I'm assuming that the LSTM is more accurate than RNN compared to the RNN, right? But slower.
it can handle longer sequences, computationally more demanding. Yes,
But slower and much more expensive, let's say.
correct.
Thank you.
That's why they came up with the next model, and then they said, "Hey, you know what? Why do I even need this long-term context? I mean, if you look at it, I can solve most of my problems by just doing this one calculation, by seeing how much of this new word is important given my previous hidden state, right? The score from my previous hidden state and a score for the current word is good enough because I'm multiplying it, right? I'm multiplying it, and I can use this to to decide the output, and I can pass that, and I can keep going doing that for the next word. So that's the next big thing which happened, which was GRU, group. So group basically got rid of the whole long sequence. It combined these two into what is called a reset gate. And then it retained the output gate. Surprisingly, the drop in performance was negligible. All right. That was the next big thing, the groove architecture.
Professor, so I just want to clarify. So the LSTM is the advance of RNNs, right?
Yes.
And then what is the TANH activation again?
TANH activation. So the TANH activation, I think we discussed this during our neural networks. TANH has a max value between -1 and 0.1. So part of the exploding gradient the problem was if you have a number 5, it just got multiplied to probably 5,000, right?
Okay.
At some
Thank
point.
you.
So if I clip it to -1 to +1, I can handle manageable set of numbers. I can work with a manageable set of numbers.
And the GRU is another like optimized version of the LSTM.
Of the LSTM, where we got rid of the long term, it's gated recurrent unit, and we just kept repeating we combined the two gates into one reset gate and one output gate. So we said, I don't even need this long term context at all. By using just the hidden state and the weight of my current word, I can actually make a prediction for the next word, which is very very close to RNN. So the GRU is actually a gated version of the RNN. That's why we call it gated recurrent unit.
Thank you.
Okay. And then people came up, I'll just take 5 more minutes. Okay. And then people came up with unidirectional LSTM. And then people came up with bidirectional LSTM because people thought, okay, sometimes I need to know what is going to come later in order to predict the word correctly. Okay. Sometimes future context is also important. So this thing came called bidirectional, where you would read a sentence from the first word to the last word, and also you would read the sentence from the last word to the first word, and you would try to predict the previous token, right? And based on these two weights, you would actually do a sentence prediction or do a summarization or translation, any of these jobs. Okay. Now, the next big version of this was something called attention, right? So in attention, we are not going to look at or self-attention, attention in any of these things. We are not going to look at the word sequentially. We're just going to see how each word in the corpus is related to every other word within the corpus. Does it sound similar, familiar? This is the core for our embedding model. Okay, but the concept is going to be the same as we did for your RNN, all these recurrent networks. So instead of using a sequence to predict the next word, we are going to see how this word sits with every other word within the corpus, and using that, I'm going to make a prediction. And now this opened up a huge possibility for me, right? So now I'm not only looking at the sequence, I'm seeing how this particular word is related to every other word within the corpus. I'm using that information to predict the next word in addition to the previous word. So if I say, the cat sat on the, okay, the next word is going to be predicted based on not only the word the and the sequence, but also on the word the in relation to every other word within the English language. Right? So if I want to complete the sentence, the cat, the next word is not only dependent on sat, it is also dependent on every other word that cat is associated with. That creates a huge possibility for me, right? That is the basis for your embedding, self-attention, transformer, all of these. Okay, and that is also your basis for something like your sequence to sequence architecture or your encoder decoder model, where you have an encoder. Now, the encoder is a very generalized term. The encoder can be an LSTM encoder. It can be a transformer encoder. Most likely nowadays it is a transformer encoder. But the concept is old, okay? People use encoder decoder architecture when they were working with LSTMs in 90s and 2000s and all that. It just got a new tag with the transformer architecture. So if you implement a transformer architecture for the encoder task, and you create a corpus, you come up with a single vector which basically captures the whole sequence of words in your encoder. Okay, and then you use this vector to make a prediction in another language, or the decoder will be the summarization task or language to language translation. But it is basically, it has compressed everything within my encoder space into a single vector. And this is the bottleneck using which I am making the next stage of prediction. Okay, so for my neural network, I just add a transformer block, which is going to say, okay, for this sentence, this particular word is going to be important. So pay more attention to it. That is the attention, no, the attention block that I keep adding to my neural network. So the neural network is there, that the attention block is there. You can add multiple blocks of this and then create a neural network, make an encoder, make a same thing in your decoder, and try to decode what is there within your encoder using the context vector.
Professor, so
Yeah.
so the block with attention is actually a block, right?
Mm.
Like
Yeah.
So it's right there, and it's on one hand it gets summarized with the context, and on the
Yes,
other hand, that one looks at all of the previous things and look at like the bigger picture in order to make better prediction.
correct. So the attention block is the evolved version of the hidden state. So the hidden state became the gate, and then the gate became like a mammoth form of it was the attention block. It really said which part of the sentence is useful.
Okay.
Okay. So that I think effectively brings us to the end of the session today. Sorry, I took 5 minutes extra. Stop share. All right.
Thank you.
So next session will be a lab session where we will also discuss reinforcement learning and yeah, so that's pretty much it. I hope you are able to appreciate the jump to the transformer based on the neural network. Remember the terms that we learned in ANNs, backpropagation, weight updates, Adam optimizer, regularizer. It is the founding block for all the LLMs that we have up until today.
Professor, out of curiosity, do we have like a quiz or anything so that we can review one of the terms so that it will be in our long-term memory?
I can create a cheat sheet of some sort. Yeah.
Thank you.
Yeah, sure.
Yeah, Professor, cheat sheet will be help a lot. A cheat sheet. Yeah.
A cheat sheet. Yeah, sure. Okay.
Thank you.
Definitely. Yes.
Professor, would you be checking your emails? I just have a couple of questions. It's better if I ask you in an email as opposed to.
Yeah. You have my email, rsiddharth@gmail.com.
All
I
right.
think I check it almost every day. Give like 1 or 2 days for me to respond.
And if you don't respond, I'll send it again.
Yeah, sure. Yeah.
Thank you,
Professor, I
Professor.
have a question. So,
Yeah.
as you're aware, like we are taking BERT as our topic, and do you expect us to give an intro to transformers, or we can assume that transformers is known?
How much of you can do within the 10 minutes? Try to do that.
Fine, thanks.
And one more question, sir. When we would, so we will be explaining the application uh, topic that we. Is it the area of the application or the architectural blueprint that we need to present for the topic?
Yeah. Also, how can you explain an application without talking at least one slide as to what extra? Like
Yeah,
I
that's
didn't
what everyone.
explain.
Yes,
I didn't
exactly.
explain the loss function and all that, right? But I said what LSTM brought to the table. So just that one slide would be good.
Yeah, that's what my dilemma. So basically, when we say application, so there could be a lot of application. There could be a lot of areas where the same model can be implemented.
Yeah.
But what exactly it brings different than the others? That is exactly what I'm expecting. If I'm not wrong, right?
Yes. Yeah.
Okay, perfect, sir. Thank you.
For example, Professor, when we take the BERT, like we can talk about the sentence BERT, digital BERT, as well as Albert, such kind of things to illustrate as an application. Is that right approach?
Yeah. Different variations of it where you use it. Yeah.
Okay. Thanks.
All right. Thank you, everyone. Thank you for staying till the end. Meet you next week.
See you.
Thanks for that.
Bye bye.
Thank
Thanks,
you.
Professor.
Bye.
Thank
Goodbye.
you, Professor.
Thank you.
Bye.
Yeah, bye-bye.
Thank you, Professor.
Thank you.